Good afternoon. This is Professor Stack, and this learning unit is presented to you from Montana Tech in Butte, Montana. Good afternoon. This learning unit will cover analytical methods, and it is a follow-on to the first lecture and takes a closer look at some methods which have limits of detection and how that feeds into your determination of the minimum and the maximum sample volume that you wish to take, which is determined by your sample time, and the selection of which flow rate best fits your sampling needs. So for this particular learning unit, I'm going to reference a method that is method 5512 for pentachlorophenol, and this was a widely used pesticide. Our learning objectives are to expand the information on how to use an analytical method to better determine your sampling protocol, and that there is some analytical sensitivity which has to do with the lowest amount, the lowest mass, or the lowest volume that can be detected, as well as the lowest amount of a substance that can be repeatedly measured. And there is a difference between the lowest amount that can be repeatedly measured and the lowest amount that can be accurately detected. And we can find this in the analytical sensitivity and the limited detection of each specific method. And in understanding this will help us determine our minimum and maximum sample volume, or at least understand why it's important to stay within a specific range given your sampling time and your flow rates, because all of these play together, because ultimately your sample volume is determined by your flow rate and your sample time. And if you do not pull in enough air, you may not have enough material in the air that can be repeatedly measured at the laboratory at a level that you wish to get it measured at, whether that's at the permissible exposure limit or some other lower method such as an action limit or lower occupational exposure limit, maybe a NIOSH REL. So when we start talking about an analytical method, I think this visual really helps you to understand the difference between the limit of detection and the limit of quantification. And that is, this specifically has to do with the sensitivity of the equipment that's being used to either extract or weigh or somehow detect the amount of the chemical on the filter or in the liquid medium. That methodology and that machine has a certain degree of sensitivity, and it is highly accurate within a specific range. And this is the limit of quantification. And this is where the technique within the analytical method could not only repeatedly detect, but repeatedly measure the amount of substance that is present from the filter or from the media. So these are two different specific terms. The analytical methods, our methods that are NIOSH methods, will list both precision and the limit of detection. When we are evaluating as industrial hygienists how sensitive the method is, will it detect a level at or below the permissible exposure limit, or how far below the permissible exposure limit will it detect? We use the limit of detection when we're taking a look at our analytical method. So the limit of quantification is the lowest quantity of a substance that can be reliably measured, and generally this is 10 standard deviations from the blank. Whereas the limit of detection is the lowest quantity of a substance that can be distinguished from the absence of no substance, and this is generally 3 standard deviations from the blank. I think as industrial hygienists, when we look at analytical results that we have gotten back from the lab, it makes more sense to us practically than it does through the definitions of the limit of quantification and the limit of detection. But here you can see that our lab results will give us results that are less than a numerical value, which means that we should not use these when calculating a time-weighted average. We can sometimes use results that are between the limit of detection and the limit of quantification. We call these censored results, and there's a methodology for the use of those. And here we could see that for lead. We found something. It was above the limit of detection, but it was below that limit of quantification where it could be repeatedly measured. Whereas here with arsenic, beryllium, and cadmium, some was found, but it was below a numerical value, and therefore we would not use that in our calculations of a time-weighted average. And again, how important it is for this sample volume, this air volume, it is reported by us on our chain of custody. It's ultimately how much we pull through our sampling media, and we want to make sure that there is enough air there to reach the sensitivity that we need depending on how we are going to evaluate workplace exposure. And so, and this is another example of looking at results back from a laboratory for aerosols or particles. So this is for respirable dust, where both quartz fraction was analyzed using method 7500, and because the sampling methodology is exactly the same, you can also take the overall weighted sample and not the fraction and evaluate against respirable dust. And so you could see that here these results are between the limit of detection and the limit of quantification and have a higher analytical uncertainty associated with them. So we would have to be careful when we were using these results. And there is a learning unit further on within the course which looks at censored data. And then these results here, we would consider them below a numerical value where they couldn't even be repeatedly detected, right? And then we have, of course, non-detect whenever there is a true non-detect. And this is the method for, this is the method that is used 0600 for particles not otherwise regulated. And so we had a flow rate here. And you can see that this tells us that we need to pull at least 20 liters of air to be able to measure the OSHA permissible exposure limit for respirable dust. That's what's being highlighted to you within that area of the method. So this learning unit, we are going to use method 5512 for pentachlorophenol, and it was used as a herbicide. It actually is called a biocide, which is a substance intended to destroy, deter, render harmless, or exert a controlling effect on any harmful organism by chemical or biological means. And as you know, these are now pretty well regulated. It's also found in wood products used as a preservative. So it does even have a skin notation associated with it, which I thought was interesting. So I wanted to use a method that doesn't come common to probably most of us in occupational safety and health, chemicals with skin designations. So when we're looking at the method, you can see that you would use a bubbler, and we do have impingers here at Montana Tech that you can take a look at when you come for the sampling class if you've never used an impinger before. This has, because it is a vapor, and most vapors you have to sample at a low flow rate, or you pull the vapor through the media too quickly for it to actually adhere or adhere to the media. And so this has a very low flow rate, 0.5 to 1 liters per minute. And you can see that we need to sample for a long enough period of time to pull at least 48 liters of air, and this will allow us to sample at the occupational permissible exposure limit. If we pull less than 48 liters of air, we will not reach the occupational exposure limit. So we're going to use this method, and hopefully it'll help you understand the different terms that are used and how you can use it when you're setting up your sampling protocol. So for our minimum sample volume, this is the minimum amount of air that's pulled through a media for accurate lab analysis. And most methods, although not all methods, list a minimum sample volume. Some of them list a maximum sample volume as well. And that's so that if you were pulling air at the highest level, that you wouldn't overload the filter, and then you wouldn't be able to use it. Or in this case, you wouldn't, well, yeah, it would still be a filter, even though this is interesting. You can see how you ship this in ethylene glycol after you sample. And so not all methods have a maximum sample volume. Most of them have a minimum sample volume, and not all methods have a limit of detection associated with them. So in this method will actually measure the permissible exposure limit of 0.5 milligrams per cubic meter if 48 liters of air is drawn. And that's if the sample contains concentrations below this value, the analytical analysis will not be accurate. So I want to say that one more time so that you can understand that if you only pulled 48 liters of air and there was a concentration in air below 0.5 milligrams per cubic meter below the permissible exposure limit, this method would not accurately detect the material, the chemical. In order to ensure that your analytical method can go down low enough to the action limit, or maybe even 10% of the permissible exposure limit, you have to take a look at your sampling volume, your minimum sampling volume, and the time in which you're sampling. So we'll move forward now. So how do we know we have reached at least the limit of detection that can be repeatedly measured when we're sampling for different time periods? Well, we can just look at using our simple formula of Q, which is your liters per minute. That equals, of course, volume over time. And if we use the minimum flow rate of 0.5 liters per minute, and we sampled for 96 minutes, we would pull 48 liters of air. And so the minimum sample volume ensures that the PEL is evaluated if the concentration in the air is 0.5 milligrams per cubic meter. If the concentration in the air is less than that, then 48 liters may not be enough air to be able to detect what that concentration is. So the question remains, what is the minimum sample volume if we don't know how much material is present in the air, if we don't know what the mass of the material is, if we're not sure whether it's at the PEL or something below? How do we know what our minimum sample volume is? And when this comes into play is usually when you're doing this integrated sampling and you want to take 2 or 3 samples throughout the day, or you want to take a short-term exposure limit. and be certain that you drew enough air through the sampler to be able to reach this level of analytical sensitivity. And so to calculate the minimum sample volume, I'm using the formula that was available from the Qualitative Industrial Hygiene Manual, which is sample volume in liters equals the analytical sensitivity, or the limit of detection of the method, in micrograms, and that is divided by the concentration that you wish to measure. And this one is a little bit difficult to get our head at what this concentration is. So if you wanted to ensure that the analytical sensitivity would be met at the OSHA PEL, then our concentration would be the OSHA PEL. But if we want to measure something much lower, a different percentage of the OSHA PEL, then we use that in the denominator of our calculation. And now, just having this formula, I'll go forward and do a calculation for you to show you how to calculate the minimum sample volume given some unknown concentration in air. So we're going to do a calculation to determine our minimum sample volume to reach some percentage other than 100% of the permissible exposure limit. So to use this formula, you have to choose some percentage of the permissible exposure limit. And just arbitrarily, I'm going to choose 25%. So the OSHA PEL in this example is 0.5 milligrams per cubic meter times 0.025 to give me 25% of that. And it equals 0.125 milligrams per cubic meter. And our formula is really straightforward. It always seems like the units don't work out, but I do prove the concept that the units work out because of the conversion back and forth from cubic meters to liters and micrograms to milligrams. The math works out if you use sample volume in liters equals your analytical sensitivity in micrograms over your concentration in milligrams per cubic meter. So our analytical sensitivity here from our method is really hard to see, 8 micrograms, and we want to reach 25% of the OEL. Simply divide. So if we pull 64 liters of air, we'll reach, with the limit of detection being 8 micrograms per sample, we'll be able to accurately measure 25% of the occupational exposure limit, which is 0.125 milligrams per meters cubed, per cubic meter. So I just calculated the minimum sample volume required. So now we can make sure that we run for the appropriate amount of time. So we have a flow rate of between 0.5 to 1 liters per minute. And if we put it into our formula, you can see that if you ran your pump for 64 minutes, you'd pull 64 liters of air at 1 liter a minute. And if you ran your pump for 128 minutes, then you would pull 64 liters of air at 0.5 liters per minute. So let's do another example where we take a look at our maximum sample volume. In this example, our maximum sample volume is 480 liters. So if I set my pump at 0.5 liters per minute and the maximum amount of air that I'm allowed to pull is 480 liters, and I do some math to isolate the variable of minutes. It means that running for 960 minutes would give me 480 liters. So I'll never pull too much air using this method. And at 1 liter per minute, we get 480 liters at 480 minutes. And this was 1 liter per minute, not 0.1 liters per minute. Which means that this method allows us to take one full shift sample. So the question is, if we take one full shift sample, what is going to be the percentage of the permissible exposure limit that this method will allow us to measure given the limit of detection? And we can use the formula to plug in the variables in a different way and come up with an answer to see how sensitive the method will be, given that we're going to run for 480 minutes at 1 liter per minute and pull 480 liters of air. Now remember, our formula is sample volume equals our analytical sensitivity divided by our concentration. And our concentration is some percentage of the permissible exposure limit. So for sample volume, I'm substituting the amount that I wish to pull, which is 480 liters. And our analytical sensitivity is 8 micrograms. And now I'm going to solve for this percentage of the PEL concentration. So this will give me 0.0166 micrograms per liter equals 0.5 times some percentage. And my 0.5 is the OSHA permissible exposure limit. So I'm just plugging this back into my equation because I isolated the variable of concentration. And now I can once again isolate the variable and get the concentration on one side of the equal sign. Oh, sorry about that. Oops. Point. .32% of the permissible exposure limit. If I run at 1 liter per minute for 480 liters, if I run at 1 liter per minute for 480 minutes, I'll pull 480 liters of air, and this will allow me to measure to 3.23% of the OSHA PEL. So now I could just solve for that. It's 0.5. It means at an analytical sensitivity of 8 micrograms, I can accurately measure 0.0016 milligrams per cubic meter if I run at 1 liter per minute for 480 minutes. So here is the math typed out for you. If you wanted to go through it again, my calculator wasn't very visible in that last example. And this is from the Qualitative Industrial Hygiene Manual, so you can take a look at the formula that I was using and how it was described and where you're using a fraction of the permissible exposure limit. And I put on the PowerPoint slide another example if you wanted to go through it and look at if you pulled a full shift sample with a sample volume of 30 liters, would you be, which percentage of the occupational exposure limit would you actually be pulling? And so you can see how sensitive your method is. I mean, in the last example, we got down to 3% of the permissible exposure limit, which is pretty low, but you could see the importance of needing to run for the entire 480 minutes to pull 480 liters of air to be able to reach that level of sensitivity, which becomes a little bit more challenging with some of our methods when we're evaluating short-term exposure limits and we're not using direct reading instruments. I hope this learning unit has been beneficial for you. Have a pleasant day.